All right, well, thank you for coming. My name is Adam Lavely. I'm here to talk about getting up and running, Introduction to High Performance Computing on the ICS-ACI cluster. Our goals for today are going to be, first of all, learn how to submit basic jobs. We're going to do this in a couple of different ways. Hopefully you'll be able to use this information to be able to go from your own computer onto ACI with the type of job that you wish to run. We're also going to be working a little bit on understanding how to compile and some basics about parallelization. And then we'll also at the very end be talking about data movement and also the storage that we have available on ACI. A couple of notes before we begin. First of all, please feel free to ask questions. The IS Center is there for you to ask all sorts of things. We have several full-time people as well as graduate students from, I think, 7 different departments, and so even though we might not necessarily work on exactly what you do, we probably have at least a little bit of experience that we can get you pointed in the right direction. And then second, I would like to encourage you to work at this. It's not something that comes easily, something that comes quickly, and so experience is going to be the best teacher. I would recommend that you replicate the examples that we do today on your own, and then try to replicate an analysis that you've already done, something that you already know the answer for, and in that way you'll be able to check your work and be able to only look at a new way of doing things and not a new problem as well. All right, so I'm going to be talking today about a couple of different things, and I just want to briefly talk about my suggested workflow for how you should get up and running. The reason that I'm going to do this is several of these will pop up later in the talk. This is what's worked for me, and this is what I suggest as a starting point for you. You might need to modify it based on your specific needs. So the first thing that I suggest that you do is to build whatever you're trying to do in parts to be able to get what I call a minimal working example. What this minimal working example is, it's an example case that has all the functionality that you need. So every function that you would possibly call, but at a much smaller scale than your production runs. So this can be either a single job when you're going to do tens or hundreds of thousands of jobs, or it can be a, say, single processor case, small mesh version of a problem that you'll eventually be doing on thousands of processors. And so if you know the answer, that's great, but the idea is that we want to be able to test things and do this quickly, not wait very long on the queue, as well as be able to analyze whatever answers are coming back and get something new going as quickly as possible. So once we have a minimal example, then we'll start to play with a lot of different flags or options for some basic optimization. And then once you have something that's working reasonably well, that's when you really start with your full-scale simulations. So that's when you start to submit your jobs at that point. After that, you start to get into more complex optimization. So one of the things that I always suggest people do is once you have something that's working, start to rewrite individual functions for optimization techniques. We'll talk a little bit about that here today. The other thing that you can do is to swap your homegrown code for advanced subroutines. There are things like PETSI or Boost out there that are very good at what they do. They'll probably be faster than anything that you write yourself. So once you have something that's working, you can swap in those to try to speed your codes up. And then at that point, start to either parallelize and go on to multiple processors or accelerate using GPUs or some other accelerator technology. I would also like to suggest that you add as many comments to your code as possible and use descriptive variable names and function names. It's hard enough to come back to something after a week. If you're going to come back to this after a year or 2 years, you want to be able to jump in and get going as quickly as possible, not have to decipher what you had been working on a while ago. Right, so the first thing that we're going to be working on today is submitting jobs. So why should you submit jobs? In Seminar 1, we talked a little bit about ACI-I, the interactive cluster that we have that you just log on and use resources that are shared with a lot of other people. When you submit a job, you're going to have dedicated resources. These are resources that are not shared with any other users, not shared with any other tasks. And so almost always what you're doing will run considerably faster. On ACI-I, the interactive machine, there's also limits to the number of processors that you have available to you, as well as the amount of RAM that's available. When you submit jobs, you can ask for more processors and more RAM, and so you're not nearly as limited. And so we're going to learn how to submit jobs today with 3 different steps. So the first step is going to be to run something in a GUI. So we're going to do this on ACI-I. The second step is going to be to run in a background mode. So this is a batch mode. Again, we're going to do this on ACI-I. Then we're going to submit that same thing as a job on ACI-B. So we're going to do the exact same thing in 3 different ways, with the hopes that you'll be able to understand how you take whatever you're working on your desktop, on your personal machine, probably with a GUI, and eventually be able to submit that as a job on ACI-B. All right, so the first thing that we'll need to do is to connect to ACI-I using Exceed on Demand. And so I've listed the host name here that you'll type in within Exceed on Demand, which is available for download on the ICS website. You'll use your Penn State user ID and password. These work as long as you have an ICS account. And then you'll also use your 2-factor authentication. I've listed an xconfig and xstart setting here. These are typically ones that work for just about everybody. There might be something that works better for you, so if you know of something else, please feel free to use that. And then once you have Exceed on Demand open, you're going to start a terminal session. So you'll do that using the Applications menu, go down to System Tools, and then click Terminal. Right, so what we're going to look at is a simple MATLAB example. I have put this in a MATLAB file called runthis.m, and what this is just a single line that's SA objective. It's a function within MATLAB. It's going to run something. The idea isn't that we care what this is, it's just that it's something that we're going to run in 3 different ways. There is more info available about this if you'd like to look up what the call is actually doing online. And so what you're going to need to do is go over to your work directory and then copy the files over. So I have all the example files that you need located in a directory called Seminar2. So use the CP command to copy that directory to your directory, and then you'll go into the Seminar2 directory with the change directory command, and then change directory again into the MATLAB example. Once you're there, you can use more or less or Vim or Emacs, whatever text editor you like to use, to look at the MATLAB file runthis.m. You'll see that it's just the single line SA objective that I stated before. We're going to be running this in GUI mode first. So what we first need to do is to prepare our environment. The way that we'll do that is by first purging the existing modules using the command module purge. And then we'll load MATLAB. So currently on ACI we have the version of MATLAB R 2016A. So we'll load that module and then start MATLAB with the command MATLAB. Once the MATLAB screen pops up, you'll type the command run this, which is just the name of our .m file that we have, and you'll see some output on the screen. The output will look something like this. This is the first part of the output. You might have to scroll back up. When I did the screenshot, I wanted to actually be able to read the text, and so I don't have the entire output listed here. So what you'll do is just take a look at this and remember your output, and then exit MATLAB. So again, the important part isn't what we're actually doing within MATLAB, it's just that we're doing something within GUI, and then we're going to do this exact same thing. You need to remember the answer so that we can compare to the other 2 methods of doing this. Okay, so we've run this now in GUI mode, but if you notice, we really didn't interact with the system at all. Right? We did open up MATLAB and say, use this run this, just use run this. And so because there was no interaction there at all, this is a good candidate for what we call batch computing. And so why would you want to do things in batch? The first reason is that this will speed things up considerably. The GUI takes a lot of overhead, both RAM and processing power, and so if we don't have to open this up, it'll be considerably faster for us. And then the second thing is that we can script parameter sweeps. So for example, you don't give it any inputs, but we could definitely modify this to give it an input. And if we were going to do this, say 50 or 100 times, you wouldn't want to be sitting there clicking each and every time to do this, and so we could do this in batch mode and do a whole set of parameter sweeps all at once. And primarily here today, the reason why we're going to submit this in batch mode is that it's a stepping stone for submitting a job onto the batch cluster. All right, so again, we're going to clean up the environment and load the Matlab module, so module purge, module load Matlab. And then you're going to enter the command that I've listed out here. I'll be talking about what each of these different things mean on the next slide. The one thing to notice is that Matlab -bin does not have a space in it, but there is a space before each of the next minus signs. And when you do this, what will happen is that Matlab will give you some output on your screen. Hopefully it's the exact same output that you saw before, just without the GUI. You can also use the up arrow to get the same command that you entered before, and then at the end of this, put the greater than log.matlab. And so that will write the output of that file into a log file, which is then saved in the directory you're currently in. You can save this and look at it later. Or, for example, if you're doing the parameter sweeps, you could save each one to a log file and then compare the different log files to be able to do whatever analysis you're doing with that parameter sweep. Let's talk a little bit about what you entered. Right, so Matlab or Matlab -bin, that's the command to actually start the program. And then after that, we're going to give it some different flags. The no display flag means that we won't bring up the GUI display. The no splash screen means that the little Matlab symbol thing that pops up while the GUI is coming up won't come up. We're using single comp thread, so that's a flag to enforce, or that tells Matlab to run only on a single processor. Matlab, like a lot of other programs, will try to take as many resources as are available to it, and so we need to tell it to only use a single processor if we only want a single processor to be used. The less than run this.m, so that's our input file. That's the same file that we used before. And then the greater than log.matlab, that's our output file that's saved for later. We'll be able to use that for whatever analysis we're doing later on. So this command and these flags are particular to Matlab, right? So all programs are going to operate a little bit differently, but these are the sort of things that you're going to be looking for when you look through your program's documentation in order to be able to switch from some sort of GUI mode to some sort of background mode, to the batch mode. And so I would suggest that you search through the program's documentation and then also just Google around. Something that we've often found is that there might be another university that has a program that does very similar things to what you're doing, and so they might have instructions for how to do things in batch mode. A lot of times you can find that very easily with some Googling around. And again, when you're trying to do this with your own thing, start with that minimal working example, right? Try a small test case before you really try to do anything big and beefy. Right, so the next step, right, so we've done something in GUI mode and we've also done something in the background in batch mode, is we're going to submit this batch job onto the cluster. And so before we get started, we're going to take a look at the submission script. And the submission script consists of two different parts. So the first part are the PBS directives, and then the second part are the commands. So within the PBS directives, really what we're doing here is telling the scheduler what resources we require. And so the scheduler will then look at this and look at what's currently running, what's available, what's on the queue, and will give you a start time as well as start and end your job when the resources are available. This is how you can get the dedicated resources that are not shared with anybody else. All of the PBS directives begin with #PBS, and these are only at the beginning of the script. So as soon as you have anything that's not #PBS or not a comment, then the PBS parser will stop reading after that. So even if you're changing the wall time at the very end of your script, it's not going to do any good. These have to come at the beginning of your submission script. And then when you are giving these resource requests to the scheduler, if your job goes beyond the resources that you're requesting, it's going to be killed. This can be in memory, this can be in wall time. We'll be talking a little bit about how to both estimate those as well as how to put in different things in a couple of slides. The second part of the submission script are the commands. And you'll notice that when we look at this, that these are very similar to what we've been using before. They're the exact same as what you have done for the batch operation in the previous example. The one difference is that you do have access to the PBS variables. So when your job starts, several environment variables will be created based on the job itself, and so we're able to take advantage of these. And so our basic commands are to load the right modules, go to the correct location, and then actually run what we're trying to do. So take a look at the submission script that I've prepared for you using more or less or Vim, Emacs. It's called matsub.pbs. So I have here the contents of this submission script. You'll notice that the first 5-6 lines are the PBS directives, and then after that we start to get into some commands for what to do to actually run the job. This particular job is requesting a single node and a single processor per node. PPN is processor per node. And you'll notice that the PBS directive, each of the directives have a flag to tell it what sort of directive that it is. I apologize for the font here. These are lowercase l's. So the L is a request for the nodes in PPN as well as for the wall time in the PMEM. So our next request is for a wall time. We're asking for 2 minutes here. So the way that the time is given, the last 2 digits are seconds, the next 2 digits are minutes, then you can go hours and days and weeks. The number of minutes are not limited to 60. You can put 600 minutes if you like, and it will read that as 600 minutes. You don't necessarily have to put it in hours. The next PBS directive that's given there is this PMEM. So this is a request for the memory per processor. There's a couple of different ways to request memory. I suggest that you use PMEM because this does give the memory per processor, and especially if you're doing multi-node jobs, this is by far the best way to do this. The other available ways to request memory are to use MEM, which is the total amount of memory. If you're on a single node, this can work pretty well. You can also request VMEM, so this is virtual memory, and then PVMEM, which is the virtual memory per processor. However, the PMEM is going to probably be the best option unless there's something wrong going on. And then the last thing that we're requesting here is that we're requesting to use the open allocation. So every Penn State faculty, student, staff member has access to the open allocation on ACI-B. Depending on if your research group has another allocation, you may or may not have other resources available to you. Right, so those are the PBS directives. Those are things that are new. You'll have to modify those a little bit for whatever type of job you're submitting. And we'll talk in a few minutes about some ways to estimate what those parameters should be. The rest of this script is the commands that we're actually going to be using. I put in a couple of the echo statements at the beginning and end. So the first one tells us where the job is running and when the job starts. The second one tells us at the very end, the very bottom line there, tells us when the job ends. These can be very helpful in allowing you to find out if something is going wrong. You know, for example, if you know that your job should only take a few minutes and it's taking much longer than that, you'll be able to see that based on the start date and end date, and not necessarily have to wait for the system to kill your job if you're not going out of your requested resources. All right, so back up to the next portion of our job commands. We have the module purge and the module load, just like we were doing on the command line. And then the next one is a little bit different, right? So we change directory to the PBS_O_workdir. I mentioned before that when you start a job, you have these PBS environment variables that are available to you. This workdir is one of those environment variables. By default, when your job starts, it's going to start in your home directory. Just like when you first log on to the system, you first go to your home directory. And so we need to go to the working directory where the files that we're going to be reading in are located, as well as where we want to put the files that we're writing out. So this PBS_O_workdir is that directory that we submit the job from. So if we change directory to that, we'll end up in the correct directory. And then we'll run the job itself. This is very similar command to what we were using before when we did it in batch mode. You'll notice here that we're writing this to log.mat. And the reason that it's a slightly different name for the output file is so that you can compare the two if you'd like to. All right, in order to submit this job, we have to be on the ACI-B cluster. This is our batch machine. You cannot submit jobs from ACI-I. So we have to SSH to ACI-B. If you're already on ACI-I, you can just use SSH to get over there because your username is the same between the two systems. If you're logging on from your own machine, you may need to put your username at ACI-B if the username on your local machine is different from the username, or is different from your Penn State Access ID. So then we'll be submitting the job. So first, change directory to the directory where we're trying to run this from, and then use the command qsub matsub.pbs. So qsub is to submit the job to the queue, and then once the job is submitted, we can look a little bit, or we can find out how well the job is running. You can use qstat, so this gives you stats on the queue, and you'll use -u in your username. This will give a listing of all the jobs that you currently have queued, running, or have completed in the past 5 minutes. It won't show you all the jobs that you've run in all time, but it will show you the jobs that have completed in the past few minutes. Because we're going to be writing out files with the MATLAB job that we've submitted, you can use ls, and I like to use the -ltrh to list these out in order of date, and so we can see when the files are being written out. And then once the files are written out, you could use something like more or less to actually take a look at what the files are. Okay, so a few notes when you're looking at the output of your job. There's going to be a system output and a system error file that are also created. You'll remember that we wrote our output from the Matlab script to a file. If we didn't write it to a file because it doesn't have a screen to write to, it would write to the system output file. There's nothing wrong with using the system output file to capture your data, but it will include some other information in there, and so if you're going to be parsing this, it might be easier as well as more consistent if you're running on different systems to always write to an output file directly from your command. These output and error files, the way that we have them set up, we'll have just some very basic information within them, but then also if your job fails for whatever reason, these are great files for you to go to. So just a couple of suggestions for ways to move forward. We've played in batch mode on ACI-I, and so I suggest that you use that to be able to look at how much RAM you're using, potentially how long your job runs, and that'll give you an idea for what to put for those requests within the PBS submission script. You can also submit, once you're done playing with that, submit to the compute nodes on ACI-B, and just within that play with some of those directives in order to get something that pretty accurately represents the amount of time that it'll take for your job to run. I typically tell people to overshoot by a factor of 2 for a test run, or even to do potentially a small test case. So for example, if you typically run with a computational fluid dynamics simulation with 1 million nodes, you can run one with 100,000 nodes, see how much time it takes, and then multiply it by 10. And then you can also monitor the job using the time command. So there's a time command that's available on both the ACI systems. You can use it with /usr/bin/time, and then you just put that in front of whatever your command is. So here I'm using it with some random Python command that I have. You could put that /usr/bin/time in front of the Matlab command that we were using before. This will give you some statistics both on the memory as well as on the amount of computational time that it's taking. The nice part about this is that it tells you the difference between the computational time, the time that the computer is actually using to run whatever task you're giving it, as well as or the difference between that and the amount of wall time that goes on. Especially on ACI-I, where you have shared resources, those two things might be very different. And so using the USR bin time will be very helpful in figuring out what request you need when you submit to ACI-B, where you have the dedicated resources. So I mentioned before that all users are able to use the open queue, but then some users have paid allocations that are also available to them because their research groups have purchased these. You can view the allocations that you're a part of using the command man list funds. And I always use the -h flag, so this changes it into human readable form. If you just use man list funds, it'll tell you the allocation balance in seconds. And if you use -h, it'll give it to you in hours, and that, at least to me, is a little bit more helpful. So, for example, I'm a part of an ICS test allocation that Wayne Figuarelli, our associate director, has. And so when I run MAMList funds, one of the commands, or one of the lines that comes up is this WFF allocation. And so you can see what the allocation name is. So in our submission script, we did the PBS -A, and we used open for our sample script, but I could also, because I have access to this WFF3 allocation, put this there. And then there are two numbers at the end of this. And so the first number is the full allocation hours. So if you had burned any hours, this is how many hours would be available to you. And then the second number is the number of hours that are currently available. And so you can use this to be able to see if your job will run, if you have available compute time. This information is also shown when you first log in to ACI-B. You can also find out a little bit more information about the allocations using the command mamlist accounts. So again, our example with Wayne's allocation, so that the name of it is given first. There's either true or false to tell you if the account is active. So because ICS offers try-ACI allocations that are only good for a short period of time, you might have many allocations that are there but that are false because they've expired. There's, after the true or false for if the account is active, then there's what the actual reservation is for. And so here it's 2 at 20, so that's 2 nodes at 20 processors per node. And then there's an end date, so this allocation runs until April 30th of 2018. And then at the very end, there's also the node type. So ICS-ACI has basic, standard mem, and high mem. This particular allocation uses the basic mem nodes. So the reservation on Wayne's allocation is the 2 nodes at 20 processors per node. And this is an accounting way for how we keep track of what the allocation is on the system itself. So each of the allocations have reserved nodes at any given time on the system. So with Wayne's allocation, there's 2 nodes that are reserved for Wayne's jobs, or for the jobs that are submitted to that allocation. So all of the jobs that are submitted to that allocation need to fit on those if they're going to have the 1-hour guaranteed start time. So for example, if somebody else on the allocation currently has 40 processors worth of jobs running and I submit jobs, then they won't fit on those reserved nodes, and so they'll be able to run in burst mode. And this reserved nodes is also important because the reservation is there primarily with the processors, but also with the RAM. So for example, we have 2 nodes at 20 processors per node within this allocation. If I submit 2 single core jobs that are each asking for all of the memory on each of those nodes, there might only be 2 processors running, but because no other jobs can run on those reserved nodes, any other jobs that are submitted will be run in burst mode. And one of the other difficulties with understanding if your jobs are running in burst mode or not is that jobs do not move. So for example, if the 2 nodes, 20 processors per node, are both full, and I submit another job, it'll start running on a node that's not a part of the reservation. And if those first 2 jobs both finish, my job is not going to move to the reserved nodes. It's going to stay on nodes that are reserved for some other group. And so it's still running in burst mode, even though it might be the only job running at that particular time. So the open queue jobs can run on any open nodes, and because they might be running on nodes that are reserved for some group, if that group submits jobs and needs those resources, those jobs will be preempted. So that's how this grade model works. You can see what jobs are actually running on any particular allocation, running or queued using the show queue command. And with that, you'll use the -W flag and then list the allocation with the account input. And so just a few rules of thumb for running your own jobs. I suggest running on as few nodes as possible for speed. So the communication between processors is considerably faster than the communication between nodes. And so the fewer different nodes you're running on, the faster your job will probably run. If you are memory bound, then start to use more nodes so you have access to more memory. But again, this is going to be a small subset of the jobs, and most users should be running on as few nodes as possible. Then even if you have an allocation, if you have some runs that aren't high priority, or you know you're not going to get to them anytime soon, you can use the open queue. Just because you have an allocation doesn't mean that you have to use that for all of your runs. All right, so the last part of this talk is what to do for moving forward. We've talked about a lot of different things today. Hopefully you're able to get started. We do have some onboarding documentation in addition to the training seminars. We're expanding the support portions of our website. If you do have technical questions though, and you can't find some answers online, feel free to contact our IS Center. You can log on with our portal, send us an email, or give us a phone call during standard business hours. And then also, Google around. A lot of the things that we've been doing are not things that are particular to ACI or to Penn State. These are things that are common. The Linux commands like rsync or scp. There's a lot of great online resources available for those. And then there's a lot of other good HPC centers around that run batch systems. TAC or the Ohio Supercomputing Center, University of Minnesota has a great website. These resources might be very helpful for you if you're looking for things that are particular to your domain. Search for a university that does what you're doing, and maybe their HPC center has some specific help for the types of codes that you're doing. Thank you for your time. Again, if you have any questions, feel free to contact the IS Center, and happy computing.